All right. So today I'm going to talk about page rank algorithm and how you can do it in Rust. And the page rank algorithm was first developed by Google to rank web pages based on the relevancy and importance. And I'm going to talk about how the concept of damping is also used in PageRank. You can see this right here in this struct. I use damping and I also use iterations here. So first up, inside of here, look at the damping factor. And this is accounting for the fact that not all surfers will continue clicking indefinitely. So the number of iterations is the number of times an algorithm will run to actually stabilize the rankings. And the other thing that we have as well is a new method here. And this new method will create a new instance of PageRank. And then if we look at the rank method itself, this is where the main algorithm is implemented. It takes a reference to a graph as an argument, and it returns back a vector of F64, right? So this in particular is going to have everything we need in order to do PageRank. Now, the rank method itself, it starts off with initializing the page rank of each node, and in is going to be the total number of nodes that are in the page rank. Then the method enters a loop that will run for a number of iterations, and then it'll calculate a new rank based on the old ranks. And then for each node, it's going to distribute its rank over its outbound links here. And then finally, after the distribution, the ranks are updated with the damping factor, and this makes sure that there's always some rank left, even if a page doesn't have any inbound links at all. There we go. So now to run this, all we have to do is get a graph of a vector of vectors. And so in this particular scenario here, we can see that ESPN links to the NFL and NBA, NFL links to ESPN, NBA links to ESPN, UFC, et cetera, et cetera. And then this allows us to kind of get things going here. And then we also mean the indexes as well. We have an initialization of the page rank with some factors here like the damping at 0.85, the number of iterations. And then again, this is the thing that goes through and calculates it. So really pretty straightforward algorithm once you walk through it. Let's go ahead and run cargo run here, and we'll go ahead and take a look. So what's happening here is that the page rank of ESPN is 0.4 Q, the page rank of NFL is 0.22, the page rank of the NBA, UFC, MLB, etc. So what this says is that the page rank is a link analysis algorithm used by Google, blah, 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 blah. So in a nutshell, that the higher the rank, the higher potentially we would put this into a search index. So what's kind of fun about this is you could use this to implement your own type of search algorithm in your organization, maybe for documents or maybe email messages or customers, et cetera. You could figure out a way to rank something by how well connected they are inside of a network. And again, it's pretty straightforward to do with the just kind of basic Rust here. The only thing that I used that was out of the box, other than vanilla Rust, was text wrap. And if we take a look at this right here, the text wrap, all it does, if we go back to the code here, is that it makes a nice, wrapped up explanation here that wraps it at 78 characters per line. So if you did want to print something out that didn't spill out into, past that particular margin, this is a great little tool to use. And that's why I did it, is so that I was able to print out this nice little description of what the PageRank algorithm did. All right, in this video, I'm going to demonstrate how to find the shortest path between two landmarks in Lisbon, Portugal, one of my favorite locations in Europe. And I'm going to use Dijkstra's algorithm here. Dijkstra's algorithm is a classic graph traversal technique for finding the shortest path from a single source node to all the other nodes in the graph. So this would mean, for example, if we have lots of different locations that you could traverse to, what would be the shortest series of nodes to traverse, and then what is that, the actual distance. In this case, I'm going to be finding the shortest path between Bellum Tower, which is right by the water in Lisbon, and Lisbon Cathedral. So first up, I'm going to use this pet graph here, which is a nice graphing library, and I've installed it right here inside of Cargo. And what also is cool is that I'm going to look at an undirected graph by using graph initially right here. So right here's the undirected graph here. And again, because of Rust excellent typing system, I don't have to worry about, lots of errors that could occur. I've got this strategy all laid out for me exactly what's going to be included inside of this graph. And then in terms of adding the nodes here, first up, we just say let Bellum Tower, and I just have that node. I say let monastery, I have that node. And then finally, I can even extend the graph by going through here and adding the distance. So I can say Bellum Tower to the monastery is going to be 1, Bellum Tower to the Electractory is 3, et cetera, et cetera. And then what's nice about this is I can put this into the node map, and notice how it says Dijkstra right here. Well, this is included inside of the pet graph library here, so I don't even have to write up that algorithm. It's able to do it for me. And then finally, I can say, basically give me the shortest distance between these monuments inside of Lisbon, or, key tourist sites inside of Lisbon. And let's go ahead and run it. So if I go ahead and I run this, I type in cargo run, here we go. We can see the shortest distance from Bellum Tower to Lisbon Cathedral is going to be 8 kilometers, right? So this is what's really nice about building out something with a, well-known algorithm, is that I'm able to, solve real world problems with this. So this could be something, again, that someone that was a data engineer or machine learning engineer, or maybe doing something with logistics, they could build this out themselves. They could count on the fact that they're going to get incredibly good performance. And again, to deploy it, it's going to be trivial, because I would just take this binary, push it somewhere, and it could run with extremely low amount of memory. And again, it's an optimized algorithm. So there's a lot to like about building these really classic problems and solving them inside of a Rust solution, and then distribute it with a binary that is extremely efficient with C-level type performance, but yet safe, because it has all of these built-in safety features with the modern Rust language, which is, a very new modern compiled language. All right, here we have some committee detection with Neil4j, which is a graph database, and they were able to detect trolls in tweets during the last 2016 US presidential election. So what I've done is I've gone over to Rust here and implemented some ways of detecting these communities by writing pure Rust code. So what we're going to do is we're going to go into the world of community detection with social networks, focusing on these Twitter users. And so I took some real data actually, and also mixed it with some hypothetical data. And these Twitter usernames are going to be using the community detection module that I wrote. So let's go ahead and take a look at Layab here. You can see here, these were some legitimate troll accounts that I was able to capture. And then at the very end here, I put in some fake community here. So the idea here is that we're going to model another community that I'm going to detect as well by, the subsequent tweets here are going to detect who is going to be associated with another user because they're retweeting their content. And how are you going to do this? Well, if we go back to the code here, we're going to import the code first, and this is going to be the data set that I'm going to use, which is the Twitter usernames. And then we're going to use this pet graph library, which is useful for both including algorithms as well as doing graph structures. And we're going to use this Khosrowshahi's algorithm to detect strongly connected components. So this is really the trick here, is that this will detect strongly detected components in a graph. And then we're going to use a hash map to store, essentially who's talking to who. And then if we go through here, first we're going to create the graph, then we're going to store the node indices by username, and then we'll iterate through that other file here, which has all of the usernames here. So this is a user, and then the next is dimension. So we're going to add those nodes to the graph and to the hash map at the same time. Finally, we add the edge to the graph, and this would be what we would call a retweet. And then this algorithm is going to detect strongly connected components. So pretty slick here, in that all we're able to do here is to put them into a vector, and then each subsequent user is assumed to have retweeted the other one. And so we can easily design a community detection algorithm that's very efficient. And we're going to say for a component in SCC. And again, this is the discovered community. Go ahead and print it. And you could put more, descriptive statistics if you wanted to, like counts of nodes, or even maybe dynamically generate a name for the community you've discovered. This is, again, a very small sample set here where I have some legitimate trolls that were used in the Neo4j data set that was discovered by NBC News, but I also have a fake one created here just to show that there's a difference between the communities. So all we need to do is cd into this directory here. I'm going to go ahead and go to community detection, and then I'm going to type in cargo run. And you can see that it was able to easily discover that there's 3 nodes in one community, which is journalist 1, journalist 2, journalist 3. They seem to be between very frequently with each other. And then we find, again, the legitimate troll accounts that were discovered in 2016 were all in there as well. So this could really be an efficient runtime algorithm for, let's say, a social network, or maybe a company that has lots of customers or users, etc. And you could build it completely from scratch yourself in Rust and have extremely good performance, and in fact, even distribute it as a binary tool that you could put into production. Okay, in today's coding session, I'm going to demonstrate how to visualize data using this Rasky graph library in Rust. You can see here from the official documentation, pretty straightforward. You put in a vector, and it's able to, with a few configuration options, print out a nice little ASCII graph here. So if I go over to my code here, and we look at this main here, I again go to the dependencies and add this. Next step, what I do is I configure a plot and a config. What I'm going to do in this particular example is look at several cities. So Lisbon, Madrid, Paris, Berlin, Copenhagen, Stockholm, and Moscow. And I create a vector that shows the distance from each of those cities. So Lisbon to Lisbon is 0. Lisbon to Madrid is 500 and Q kilometers. Lisbon to Paris is 1,053 kilometers, and so on and so on. Now, what I do is I print this all out using this library, and it's pretty straightforward to have it work. So let's go ahead and do cargo run here. Perfect. You can see here that at the very beginning, I give a header here that just shows people, when they're looking at the code, exactly what's happening. For example, each of the distances, and you'll see that they get longer and longer and longer. And then what's nice at the very bottom as well, I put a little metric here of the travel distances, right? So I say it's going to be in kilometers, and then this has the actual kilometer. So for really quick and easy type of ASCII charts in a Rust-based chameleon tool, this is a very compelling library, and you can put a data structure in here and really get to work very easily. So I think this is another thing to point out is it's very simple with Rust to create portable command line utilities that include charts and graphs, especially if you keep it really simple and work within the confines of what libraries are available. In this case, you can see it's a very small amount of code, and to print something that's fairly sophisticated, and we're able to communicate very well to the person that's using the tool exactly what's happening.